All right, but what I want to talk today is a joint work with Yan Guo from Brown University and Klaus Widmeyer from EPFL, and it's on the long-time existence for the Euler-Coriolis system. So this is the equation that we will consider. So the usual Euler equation, except that you have this additional force, which induces, well, and the whole point is to understand what is the effect of that. So this is the equation that an incompressible fluid would satisfy if it was in a frame that is uniformly rotating at a speed omega. And what we want to show is that if we fix the speed of rotation, then small and axisymmetric data lead to large time solutions. And what does large time solution means? Well, essentially it means almost global. So for every m positive, you can find a solution. So for every m positive, you can find a norm such that if you have an axisymmetric data, which is small enough, then the time of existence is going to be big. And so just a few cartoons to try to really illustrate what we are considering. So this is really the picture that we want to think about. We have a container here with some fluid, and then we make this container rotate. And inside we have an incompressible fluid, incompressible inviscid fluid, and we don't want any boundary conditions. And so as you can imagine, there are several ways to do this. And for us, it would be to look at the case of the whole space. So just before, why would you want to consider this? Well, this kind of problem arises naturally in a laboratory, but also through the effect of the rotation of the Earth. You naturally have some Coriolis force, and so as you change the latitude, then its strength changes. But if you stay in one of the cells, then you can imagine that this is more or less rigid motion. All right, and so what I said was that there are two ways that you could be in this situation without boundaries. And in fact, there are really two previous important works that are quite connected with what I'm going to talk about. And so, but in both cases, they look at a slightly different scenario, which is the case of a fast rotation. And so the first work is, well, no, actually, I probably won't describe this. So the first work is on a generic torus. So you're in a compact domain, but then this case has been studied by many people, but at least one of the main work is from Babin Mahalov and Nikolaenko. And what they show is that, so not just for axisymmetric, but for general solutions, what you can do is decompose them into a superposition of two different pieces. One of them is essentially a solution to the Euler plus some passive scalar that is advected. Then another one is a solution to a linear equation. And then, of course, you have an error term, but this error term, you can make it quite small, at least for a long time, provided that you rotate your fluid fast enough. So this is one work on this equation. Another work on this equation is on R3. And in this case, a few people, Dutifra, but I think the latest result is by Kohli and Takada. They showed that if you rotate fast enough, and starting from any solution, then you can make sure that your solution exists on a long time scale, which is, well, in this case, of the form log omega. And so if you look at this, then you can see that both of these works, they try to, or they really use two different aspects of dispersion. And so in the first case, once you're on a generic torus, you can basically make sure that most of the quadratic nonlinearity becomes non-resonant, and you can do a normal form. And this is more or less what this is saying, that you have a resonant system, which in this case happens to be the Euler equation. And except for this, you are effectively evolve linearly up to a remainder. Now, if you're in R3, then it's not so easy to avoid the resonances. But the thing that you gain now is decay. And there are a lot of different ways that you could try to use this or to express that. And in their case, they use the Strickard's estimate to show that you can gain a long time control of your solution. And so what I'm going to present is something which is really at the intersection of those two works. What we're going to do is to try to combine this information from the fact that we're talking about a dispersive equation to do at the same time to try to use the advantages of decay and the advantages of normal forms. And it's not going to be too easy. And in particular, the thing that really becomes very difficult in this case is the resonance system. And the resonance system is the 2D Euler equation for us in a certain sense. But in some sense, the point is that the 2D Euler equation is global. You have global existence for that, but not in norms that are really compatible with the norms that we're going to use. And so what we want, the one thing that we cannot do is handle that term. And so this is why we consider axisymmetric initial data, because in this case, the solution to the Euler would be to the Euler with a radial vorticity. And then to the Euler with a radial vorticity is a very simple equation. So this is really the plan. Now, and I'm sorry, not only do I not know how to make the header disappear, I also don't know how to remove some poses from LaTeX. But anyway, the other point, yes, so I need to make a disclaimer. No boundary will be crossed in this talk. This is not about free surfaces, unfortunately, but variants of these questions are very relevant and have been studied a lot for free boundary problems. And in fact, this fact that the Coriolis effect really stabilizes fluid is something that is quite classical, and that there is a huge literature on that. And well, so if you think of other different directions, there would be a lot of work. But for us, the two most relevant are the ones by Babin, Mahalov, and Nikolenko, and Kohli and Takada. All right, so now let's get back to this equation, this Euler-Coriolis equation. So just to remind you, this is just what you would get if you combine Newton's law. So this is the acceleration is equal to the sum of the forces, and you have the usual contact pressure forces and the Coriolis force that comes from the fact that you're in a rotating fluid. And maybe just one thing. So at least for me, for a long time, I thought it was a little hard to believe that just moving into a uniformly rotating system would really make such a big difference because of some Galilean invariants. But another way to think of it, it seems to me, is that it would be talking about stability of Euler in 3D, but not of the zero flow of a flow that rotates uniformly. And therefore, because at infinity, you're forcing a non-trivial rotation, this is really what is going to give you the stabilizing effect. All right, so in fact, to a large extent, this talk is going to follow the framework that Alex presented this morning for those of you that tuned in. And so it's the same situation. We would like, yeah, so this is the bigger framework. And so what I would like to do now is to really see what are the main things that we need to understand about this Euler-Coriolis problem. And so the first one is that you have two non-trivial symmetries for this Euler-Coriolis problem. You have one that is the scaling, in which you would rescale position and the velocity, and you keep the time alone. This is because you've already forced the speed of rotation to be 1, and so you can't really tamper too much with the time. but on the other hand, you can always adjust the two others, so velocity and scale this way. And the other natural symmetry is just symmetry by rotation under a vertical axis. And so associated to those two symmetries, you have the corresponding Lie derivatives, which gives you some non-trivial control on your vector fields. And you see, we're going to be in the same situation as what Alex presented for the Euler-Maxwell problem or the gravity capillary water wave problem, where you do have a lot of vector fields. And so you would really want to use that information, but you don't have enough to be able to span the whole tangent space. And so you need some other control to be able to close the analysis. But on the other hand, at least for us, what you can observe is that because you have this symmetry from your nonlinear equation, then at least if you start with axisymmetric data, your data are going to remain axisymmetric for all time. And so this is not, well, so it makes sense to think about axisymmetric data. Okay, so this is just the standard picture of the what you have when you move to spherical coordinates, is to show this kind of interesting fact that even though we're really, the natural thing in our case is the cylindrical symmetry, because we have this axis of rotation, the two natural vector fields that we have are the scaling that is really controlling the radial derivative, and then the other one, which is the d by d theta, which is also one of the coordinates in the spherical basis. And the one that is missing is this d phi, so d by d phi. And this is really going to be the one that we try to enforce later on, except that, of course, it won't really commute with the linear flow. But this epsilon is going to come back later, and this is nothing but just the third vector in the spherical coordinate basis. Okay, maybe the most important thing to know about our problem is that it is dispersive. And so, in other words, if you think of this linear problem, this is maybe not so obvious, but it's a dispersive problem. Sometimes it's called the Poincaré operator, or its propagator is called the Poincaré propagator. I tried to look a little bit. It seems to me that Poincaré was really talking about something with a free surface. So not exactly that, but on the other hand, if Poincaré also considered this as a special case, then I would not be too surprised. But so anyway, this is just that I'm not sure about the name attribution. But this is a linear problem, and what you can do is to, once you have that, compute its dispersion relation, and you see that it's given by this. So C3 over C, or another way to think of it is that it is the cosine of phi, where phi is the coordinate in spherical coordinates. And something that is of some interest is that this dispersion relation also seems to appear in a different fluid context. As far as I understand, it at least appears for stratified fluids, and I'm not sure exactly what the connection is, or if it's just some kind of random fact. But so this is the dispersion relation, and it's a little unusual, so it's probably worth spending a little bit more time on it to understand what happens. And so the fact that it is zero homogeneous directly forces through Euler's equation that the group velocity is going to be perpendicular from the position frequency, which is something a little bizarre. And in fact, you can fairly easily get natural formulas for the gradient. You can also get reasonably nice formulas for the Hessian. So the advantage is that at least we're talking about an axisymmetric function. And so you are going to have a few zeros in the Hessians. The other terms are reasonably complicated, not too much, but at least using them, you can compute the determinant. And then you get this really nice thing that you can understand exactly where the Hessian becomes they generate. And not only this, it's also something that is quite natural. It is going to be either for frequencies that are purely vertical or frequencies that are purely horizontal. So either this is 0 or that is 0. Now, when I learned that, I thought this is going to be a very easy problem because we're in 3 dimensions. In 3 dimensions, you would expect the decay rate to be t to the minus 3 half. And so probably we're going to lose something due to those degeneracies, but you would say, even if I lose something, I should still be integrable in time. And then if I'm integrable in time, I should be able to basically bootstrap any boundedness of a reasonable norm. And indeed, what you can at least check is that you always have a 2 by 2 minor, which is non-degenerate in all of those spaces. Also, when the frequencies reach the bad regions, so you start with 1 over t decay and you say, okay, because I'm not exactly 0 elsewhere, then I should be able to get something better. And in fact, the surprising thing is that no, 1 over t is the best thing that you can do even in 3D. And at least for radial functions, you can compute exactly the solution at the origin. And there you see that this is never going to decay faster than 1 over t. So that's something a little bizarre. And on the other hand, you can also realize that this is vanishing at too high order on the corresponding region for you to hope too much more. But okay, at the very least, if you have something that decays like 1 over t, you could really expect to have almost global existence. And this is more or less what we do, what we show, except that there are some logarithmic inefficiencies that we have not been able to rule out. Okay, so now that we understand this, then we can get back to this work of Corey and Takada, or Babin, Mahal, and Nikolaenko, and look at the case of a large rotation. So if the rotation is of size epsilon to the minus 1, then we can really rewrite the system this way. And what you observe is that you're talking about a perturbation of a linear Poincaré system, for lack of a better name, albeit in fast time, and it's perturbed by a nonlinear term. And in this case, you have a small daytime, so you can make it small on top of that, although just by moving u to epsilon u, you can also make this epsilon 1 here. So this is not really where the main gain is going to come. What the main point is that this is a dispersive equation. And so if you believe that in 3D, so it's a dispersive equation and a dispersive equation in this fast time. And so if you believe that in 3D, your linear solution is going to be very small outside of a small time interval, then this small time interval is going to be even smaller in the real time t instead of tau. And so, well, so then the question is how to really make sense of this, or how to express that. And one way to do it is to do Strickard's estimate. What you can do it with epsilon equal to 1, and then just this, because this corresponds to rescaling time, when you do it, you see that the moment you choose any Strickard's norm, which is not L infinity, you're going to gain this small factor. Now, the problem is that this does lose quite a bit of derivatives, and Corey and Takada want to work at low regularity, so in H5 halves, if I remember well. So they need to do some interpolation with the energy estimates, and in doing that, you lose. When the dust settles, it seems to be the logarithm that really gives you the time of existence. And on the other hand, in the work of when you can do a normal form, then you see that doing a normal form is more or less, at least formally, like multiplying like dt to the minus 1 or d tau to the minus 1. And then just by the homogeneity, the moment you can do a normal form, you'll be able to squeeze out an epsilon in front, and then you stop. So, yeah, so this is a way to understand what happens in other cases. And what we would like is to find other ways to get the dispersive decay, maybe not through streetcast estimate. Now, something that I don't really know what to do with it, but since at least in the modeling place, it's quite important. So the small parameter in your system, there is one parameter that you can't really rescale away, and it is the Rossby number, which should be the ratio of a length scale for the velocity, a length scale for the space, and then the speed of rotation. And so there's various ways with the norm that I'll present to you that you can have something which is like the Rossby number. And in our case, the Rossby number would be of size epsilon. So this is a little bit the same as just enforcing all the scales to be 1, and then you would have this. Okay, but at least for us, so for us, this is 1, and then U is 1, and if you tally up this homogeneity, this is going to give you 1 epsilon. But I'm not sure that this is really the best way to think about it. Okay, so now maybe more about the analytical motivation for this. So one, as we already discussed, one of the interesting things about this problem is that it is in this setup where you have some vector fields so that you can hope to get a fairly good control of your solution, but not enough. So you won't really be able to only use just the vector fields. The other thing that made this quite compelling as a problem is that there has been a lot of work for quasi-linear dispersive equations, and all of them looked, except for KP1 and KP2, essentially, all of the classical ones that you can think of have a radial dispersion relations. This is true for Schrödinger, for Klein-Gordon. This is true for water waves, at least if you perturb a flat equilibrium. This is true for Euler-Maxwell. This is true for a lot of the equations. And the question is what happens when you move out of this? So ideally, you would like to only be able to express your analysis in terms of things which are just codimensions and so that are not really tied to some particular technical aspect of your equations. Or you would like to get criterions which are general enough. Anyway, and so, well, the question is what happens, at least what do you get when you have a radial dispersion relation? Well, at the very least, you start with a lot of commuting vector fields, because then everything is going to be rotation invariant. And so you already have n-1 vector fields. So the situation is quite nice there. Now, something more is that almost by definition, all of the structural properties that you're going to be able to define, like this epsilon of the place of space-time resonance output or the place of space-time resonance input, there will be, by definition, concentrated on things that only depend on the distance to the origin, and so on spheres. And so, okay, you can say, but this is just a hypersurface, this is quite normal. But on the other hand, there are a few natural questions that appear. So for example, when can a space-time resonance output become a space-time resonance input? And so that is a question about the intersection of two of those sets that you define. And now if all of those sets are spheres centered at the origin, then you see that you have this strange thing that either they coincide completely, in which case you would be fully degenerate, or they don't intersect at all, in which case you probably are quite good. But if you were talking about general surfaces, then what you would expect is that the intersection should be something of codimension too. And so, for example, in 3D, it should be still something quite interesting. And maybe those are just technical, but at the very least, these questions was addressed or started to be investigated in the linear level by Benoit and Germain, who looked at the product of 2 free evolutions for different dispersion relations. And what seems to happen is that if you are, so you need to have a few structural informations that are more or less automatically satisfied for radial function. And so this was one of the motivations to try to understand what happens when you move beyond the radial case. And in this case, we're not radial, but we are still axisymmetric. So it is probably the next thing to try to understand. All right. And so now the general strategy that we use is something that was highlighted by Alex. To some extent, we don't really go as deep in the analysis, so it's not the same. So it's not exactly the same steps. And also, we try to work slightly differently with creating a field made of vector fields. But at least the main part are the same. So the first one is to find a good reformulation to the problem as a nice dispersive system so that you end up with a good PDE that you can easily work with. The second one is to have to understand better the dispersive analysis and to try to get precise linear estimates so that you understand decay well, and in particular that you can see how weak can you make your main norm, the equivalent of the Z norm, so that you still get optimal decay, because in our case, we're really shooting for 1/t decay. The last one is, the next one is something that is not too surprising. You have vector fields, and more generally, you have a hyperbolic system. You would like to use that and be able to use this to control high order energies that would control many flat derivatives, and in our case, also many vector fields in L2. The next step is when we start the dispersive analysis. So there you really have to look at what are the technical properties of the nonlinearities that you're dealing with. And the idea here for us is going to work still on vector fields, but then through understanding better the dispersion to upgrade L2 control on the vector fields to control of maybe fewer vector fields, but in a stronger norm. And in our case, it would be an L2 norm that mimics more or less the fact that the Fourier transform is in L infinity. And then the last one, the second part of the dispersive analysis is more or less something more standard. You introduce another bit of control outside of the vector fields. So in our case, it's going to be this additional vector fields that doesn't commute. And you try to propagate control of these vector fields in L2. Okay. All right. So now let's say a few words about some of those steps. So the first one is, how do you get a nice dispersive equation starting from Euler equation? Well, the main point is that your unknown is a 3 vector. So this is 3 functions, but it satisfies analytic constraints. So you would really think that there is only 2 scalar degrees of freedom that you want to consider. But if this is the case, then you don't want to keep track of 3 functions that are relating in some way. And so you try to look at what kind of, how can I parameterize them? And then after playing a bit with the equation, you see that you can obtain a nice system, at least at the linear level, in terms of the vertical component of your velocity field and the curl of the horizontal component. And so this gives you a nice linear system from which you recover the dispersion relation. And then the nonlinearity is, well, it's what you expect for the Euler equation. It's more or less u squared with 1 derivative outside. And here I have 2 derivatives, but it's because I'm talking about some curl of u. Okay. And so once you realize that, then you probably want to take this as one of your unknown, this as the other of your unknown. You give them a name. Let's call them A and C. A, in our case, is going to be the swirl. And C is, well, C is the horizontal direction. And so after that, you need to play a little bit with them. But if you make them at the same level of U, then you get this nice property that you would want for Hamiltonian system, that your Hamiltonian is the kinetic energy, decomposes exactly as the sum of the squares of the two of the inputs that you have. And on top of this, and in addition, from you can recover A and C, and A and C parameterize you in the sense that if you know A and C, you can easily recover U. And so once you do that, now what you want to do is to express the nonlinearity in terms of those unknowns. And now things start to get messy. You get a really big expression, but after thinking about it, then you realize that you can decompose that into three terms. So the blue, the green, and the red. The green terms just satisfy all of the best properties that you might want. So let me just discard them right away. The blue terms are not as nice, but they are still quite nice in the sense that they are quadratic expression in the unknown that you have. And they contain a copy of either the phase of or 1 minus the phase, which is basically the distance or some way to measure the distance to the place where the linear dispersion relation is degenerate. And on a technical point, it also happens to be the place where you have space-time resonances. So at least those things should have some kind of null structure, which is quite nice. And then unfortunately, you also have those red terms here and there. And now those red terms, this is what they are. And as you can see, they are not going to give you any other nice property when you approach those degenerate spaces. And in fact, what you can see is that if you're looking at horizontal frequencies so that lambda becomes 0, and let's say you discard those, which you can, but it's not even so important, and you only retain these equations, then what this is exactly to the Euler equation, not really for A, but for what would be the curl of the horizontal part of U. And indeed, you can verify. So if I multiply this here, I would have dt capital A is equal to grad minus 2 of capital A, grad perp, and then grad capital A. So this is the vorticity equation. And then you have the same thing that appears here, except that in this case, then C is passively advected by the flow created by A. So this is exactly the system that Babin, Mahalov, Nikolenko found. And on the torus, they really had to isolate it. And this is what, in principle, we might also have to try to attack, but at least all of the norms that we consider are not really well acquainted with or well adapted to the Euler equation. So for example, one thing that you would want to be the Fourier transform in L infinity, but we had seen some in a previous work with Inji Zhang that in fact to the Euler is ill-posed in this norm, no matter how many derivatives you add. So it's not so easy to think of Euler in the Fourier space, unless then you really get into analyticity, but then that would be not super adapted to our setup. So we don't really know what to do with this. On the other hand, the good news is, or what we do is we consider axisymmetric initial data. And then in this case, this is the gradient of a radial function on the plane. This is the gradient of a radial function on the plane. And then you're looking at their cross product. And so this is not just 0 initially. This is guaranteed to be 0 for all time. And so we can just discard those red terms. And in fact, this is why we really need to consider axisymmetric initial data, because since this corresponds to vector fields, we could presumably get the analysis and then think of our solution as almost axisymmetric, but then we would have to face those nonlinearities. All right, so now let me go a little to the norms that we want to choose. This is some variation on the framework, the the typical framework. The main point is that we really have these degeneracies, either if the frequency becomes very vertical or very horizontal. And so we want to quantify how close our frequencies are to this. And so in order to do that, we introduce Littlewood-Paley. We want to quantify this by this parameter P and Q. And another way to see this is that we introduce a Littlewood-Paley projection for horizontal frequencies and a Littlewood-Paley projection for vertical frequencies. And so then after that, the norms that we're going to choose to control are the energy estimates norm, are just the typical high derivatives, and then H-1 norm of your unknown, and same thing for your scaling vector field. And the second step will be to use the dispersive analysis to bootstrap a lot of vector fields in L2 to fewer vector fields, but in this B norm that is more or less here to mimic Fourier transform in L infinity, but in a hopefully norm that is a bit more compatible with what would be to the Euler for one thing. And at least that is a little bit more manageable, the L2 norm of the function. But you see, this is more or less, at least if you were at frequency 1, this would be the 1 over the square root of the area of the rectangle where you're supported. And then the last step is to use even fewer vector fields, but now control not just our function in L2, but this other thing, which is this missing direction in the Fourier space that we wanted to have. Okay. All right, and so I'm going to go quickly. The energy estimates are just what you would expect. So as we have seen, we have exact symmetries for the nonlinear equation. So if you take the Lie derivatives, you get that the derivative commutes properly with your equation, provided you define it appropriately on matrices. But in any case, it would be lower order. And the advantage is that as you have in Euler equation, you can factor out the loss of derivative. And so this allows you to control an H-1 norm. And on the other hand, this is also hyperbolic, so or skew symmetric to the top order. And so you can do energy estimate to propagate L2 derivatives, L2 control. And now we arrive at the, so I should conclude, we arrive at the last step of the analysis, which is to to try to do the dispersive analysis to the, because once after using the reformulation, we have made it into a dispersive system, then using the Diabel formula, as Alex presented, we can replace that, we can express the contribution as those nonlinear oscillatory integrals. With the phase, which is, so every combination happens, and then what is good, and this is the equivalent of the blue terms in the description of the nonlinearity, is that our multipliers are one nice multiplier, which might as well be 1, and then one value of either lambda or root 1 minus lambda squared. But the problem is that we don't know exactly on which one of the unknown does it fall on. And as far as we can tell, it seems that all of the cases do happen. So you don't, it would be a lot better if we knew that this was always the output frequency, but this is not the case. And then you have to start massaging this term and to try to prove boundedness of that. And so let me quickly just say that you can make a few nice observations. So what you would want in this interval is to integrate by parts. So you can try to do normal forms. The other thing that you have nicely is a lot of vector fields. And so what you would like to do is to see if you could integrate by parts in the direction of the vector fields. And you have two vector fields. So you have to see what is, how big are they? And you have this nice property of the phase that at least if they can never be too small unless you're talking about a really small integration volume up to some degeneracies that hopefully can be incorporated in the multiplier. And so this way, it allows you to, so you can integrate by part along one vector field, and then you will have to distribute it to either of the unknowns. And if it falls on one of them, then that's basically okay, because you already had a lot of copies of this vector field, so nothing really happened there. You had information on n copies. Now you have information on n-1 copies of the scaling vector fields on that, but that's really not a big deal. But if it falls on the other one, then you have to re-express your vector field into the basis. And so you have two terms that are nice, but there will be one term that you need to keep under control. And this is why this is good to do something, but not completely strong. And for us, we use it to be able to say that we can control this term into the B norm instead of the L2 norm, up to losing a few vector fields. And then to really manage to get nonlinear control of this other non-commuting vector field, then you need some more information. But in some sense, things are not as bad as they could be. So you can use the fact that when the phase is too small, the gradient can be small, but at least you control its size, and some of it can be recovered through the multiplier, and some else can be recovered through the fact that you control some B norm and not the L2 norm. So you get better access to the size in the integral that you consider. And okay, that's the end of my talk. So maybe I should just directly thank you for your attention. I've seen that I've gone over time, so I'm sorry.